Hello students, welcome to our class Mechanics of Materials. In today's class I'm going to discuss design of beams and shafts. I'll focus mostly on the beam, and it is in chapter 11. So far we have learned a lot of about beams. In the chapter 6 we learned bending. Basically bending is basically in the bending we dealt with the beams. So the most of the beams actually are made of one. First thing, there are a few things we want to learn today. The first things is there are few parameters or few characteristics of the beam. The number one is most of the beam are made of ductile materials. Like steel, aluminium, copper, and in the structural materials in bridges or in the roads, basically they used steel structures. And in the beam we consider two type of stress. One is bending stress, and the second is shear stress. Shear stress and bending stress, these two types of stress we consider when dealing the beams. So, and the beams are usually long, so internal moment M is large. And to design a beam, that's why to design a beam usually the engineers first consider the bending. Engineer first consider bending, then check the shear strength. So we will solve a problem, then after solving that problem we will understand how this process is carried on. And so the first thing, to select a beam we need to first understand a parameters called section modulus. Okay. The section modulus is defined by S, and section modulus, keep in mind it's a geometric property, and it's not a material property. So it's a geometric property, and remember and we have discussed several material properties like Young's modulus, Shear's modulus, Poisson's ratio. Those are the material property, but section modulus is not a material property. It's a geometric property. And the section modulus, we define the section modulus by the section modulus is defined by the ratio of moment of inertia of the cross section area about the neutral axis and C. So here C is actually perpendicular distance from neutral axis to a point farthest away from the neutral axis. I'll give you more explanation on that. I is the moment of inertia of the cross-sectional area about the neutral axis. So let me explain this by a diagram. If this is a cross section of a beam and this is my neutral area, neutral plane, and C is the distance between these from the top of the top fiber, that means the outermost fiber or outermost surface of this cross section and the neutral axis. This is C, and so this is a neutral axis x, and the moment of inertia could be, so this is y, this is another neutral axis. So I will discuss later. So this, if I consider this cross section, I will take this x neutral axis and find the moment of inertia for this x neutral axis. Now so as I said, this is a geometric property. I'm going to show you an example how this geometry, the orientation of geometry affects the section modulus. Now let's consider a cross section, a beam which has a cross section. Consider a beam which has cross section, and this is the width and this is the height. And this orientation, say this orientation is A, and this particular beam is say 2, say 2 meter. Okay. And the height is 4 meter. So that means h is equal to 4 meter, b is equal to 2 meter. Now this is the orientation, and we can actually the same beam can be oriented like that. That means now this is my h, and this is my b. Now here h is 2 meter and the b is 4 meter, and this orientation is say B. So now I know the section modulus is defined I by C, and okay, the one more thing is missing there, that is actually C. The C is, if this is my neutral axis, I'm not sure how visible, say this is my neutral axis and this is the neutral axis. So okay, this is neutral axis, this black dotted line, this is neutral axis. Then the C is this distance from the top to the neutral axis. Here the C is basically, this is my C. So in that case C is, and C is basically defined, C is h by 2 and C is 2 meter. In this case, for the orientation B, h is 2 meter, B is 4 meter, and C is h by 2, that means 1 meter, right? Now so I is a section moment of inertia. The I is 1 by 12 bh cube, and AC is h by 2, right? So if I simplify this is 1 by 6 bh square. Now the section modulus for the orientation ASA is 1 by 6. Here B is BH square. So B is 1 by 6. B is 2 meter. And H is 4 square, which gives me 5.33 meter cube. Okay, 5.33 meter cube. And SB, section modulus for the orientation B, BH square 1 by 6. Now here B is 4 meter and H is 2 meter. That means, and it gives 2.66 meter cube. So clearly you can see the section modulus A is greater than section modulus B. So this actually tells this section modulus is a geometric property, and if in general if your height of the sections is more than your width, h is more than b, then your section modulus will be higher, because bh square, so h has a power of 2. Now, so this section modulus helps us to determine the beam. How? Now we know from the chapter 6, from the bending of the beam, we learned that flexure formula sigma equal to mci, right? And basically we can write this formula this way: sigma max m max c by I. For the timing, I'm writing here sigma equal to m max c I. Okay, I'm writing like that: sigma is equal to moment, maximum moment multiplied this c and divided by I. So if we rearrange this equation, say we can write sigma, okay, let me put this way: sigma mci. Okay, now we can rearrange sigma by m equal to c divided by I. Can say I divided by c equal to m divided by sigma. So this I divided by c is what? This I divided by c here, you can see this I divided by c is s. So s is equal to m by sigma. Now S required which I'm going to write this way, equal to m maximum divided by sigma allow. So required section of modulus is, we can determine by dividing maximum moment divided by sigma allow. So m max is determined from beam moment diagram. And Sigma allow is specified in design code. So there are a lot of design codes. For example, ASME design code, ASCE design code, NSCE design code. So there's a lot of organization who develop a standard design code, and we, for particular material, particular alloy, they have developed that, and we will get that value and plug this here in this equation, and we will get this sigma required in the section modulus. I'm going to solve a problem later part of this lectures, and after I solve the problem we will understand this. Now, so as I said, the section modulus, there are a lot of beams. For example, so as you said, so these are the lot of beams, which is the section. This is one rectangular, so this is box, circular cross section, pipe or tube, and I shape. So this is the most common and mostly used cross section, the I shape. This is called T shape, this is L shaped, U shape. The U shape is also known as channel, L shape is also known as angle. So there is a one more, there are other section which is very popular, that is called C section, called C section. Okay. Also the U shape is something also channel section, and the I shape is sometimes called H section, and both these two, I shape and H shape, is also known as wide section, and in your book it is actually named wide flange section, wide flange section. So these sections are very important, and the section dimensions is very important to determine the section modulus. Now we are going to solve a problem, and that problem, it's in the book, it is in the page 548, example 11.1. Okay. So let's look at the problem. So you see 11.1, page 548. So this is the problem. To say that it's a beam. A beam is to be made of steel that has an allowable bending strength of 24 KSI, kilopounds per inch square. An allowable shear stress is 14.5 KSI. Select an appropriate W shape. W shape is also known as I shape, H shape, or wide flange shape. This is W shape. And basically the W shape, let me show you which one is the W shape. So this is the I shape, is known as W shape. So we need to select a W shape that will carry the loading shown in this figure. So the first, in order to solve this problem, we need to find the reaction forces. We need to draw the force diagram, free body diagram of that configuration. So let's solve this problem explicitly. You see, this is our beam, okay, and it has a pin connection here. This is external pin connection, and there is a load here that is 40 kilopound, and this length is 6 feet. So there is a roller support, and this is also 6 feet, and there is another load from the top which is 20 kip, and this distance is also 6 feet. Now, so there's a pin connection and two forces from the top, and there is a roller support. Now first we need to draw the free body diagram that should have all the forces. So in order to do that, we need to go back to the chart. So as you see, so this is a external pin. So external pin has two reaction forces. One is in the horizontal direction and another one is a vertical direction. Also the roller has only one reaction forces, and this is in the vertical position. So I'm going to draw these reaction forces along with my loads. Okay. So this is my position. This is my position A, this is position B, this is position C, this is position D. So here two reaction forces, one is AY, AX, okay, and at B I have 40 kips, and that is 6 feet, and at position C where the roller is located, it has one reaction force, say CY, and this is also 6 feet, and at the end position D, it has another load from the top, 20 kip, and this is also 6 feet. So in the bending lecture, when I plot the bending, I said that so reaction force AX, horizontal forces, is not considered, doesn't have any uses in bending. So we can actually get rid of this, and to find the reaction force AY and CY, the first we can take a moment with respect to point A. We find the summation of moment with respect to point A, and my clockwise is positive. So this is equilibrium equation. So that is, if I write this equation, this is 40 kilopascal and multiplied by 6 feet, and this is positive because it is clockwise. Then CY multiplied by 12 feet. So CY from, if this is my A, from here to here 12 feet, and it was anti-clockwise, so it is negative, plus then third one 20 kilopascal is clockwise, and it is 16 feet away from the point A. So 20 multiplied by 16 feet equal to 0. Okay, so if I do my calculation correctly, CY is 50 kilopound. The next, I will apply the another equilibrium equation, which is summation of forces at y direction is 0, and in this case the upward forces are positive. If I complete this equation, is AY minus 40 plus CY minus 20, and this is keep, this is also keep, is going to be 0. That means, and I know CY is 50 kilopascal, so then my AY is 10 kilopascal. So I got my reaction forces AY and CY. So the next thing is, I'm going to see. So this is my A, this is 10 kilopound, this is AY, and this is 40 kilopound, and this is CY 50 kilopound, and the last is 20 kilopound. Okay, and I know this distance is 6 feet, 6 feet, 6 feet. Okay, so the next step is to find the shear forces, because we will be drawing our shear force diagram. So this is going to be my shear force diagram, SFD, and I'm going to extend this. Okay, then again after that I'm going to draw my bending moment diagram, BMD. Okay. So and this unit is, this is V, this is M, and the unit of V is kip. Okay, I will. So before drawing the diagram, we need to find the shear forces. Okay, so let's see what are the shear forces here. So shear force, so VA is 10 kilopound. Okay, kilopounds. VA is 10 kilopound shear force, V, and VB is 10 kilopound minus 40 kilopound, because at B position, when you say there is a 10 kilopound and 40 kilopounds, so and in our sign convention is upward is positive. Okay, that means minus 30 kilopound. VC is 10 kilopound minus 40 kilopound plus the 50 kilopound is upward, as you see, so it's a 50 kilopound, that is 20 kilopascal, and VD is 20 kilopascal. Okay, if I draw my shear force diagram, and V, this is unit is actually kilopascal, say kilopascal, keep. If I draw my shear force is 10 kilopascal, so 10 kilopascal, and then this is 20 kilo, then minus 30 kilopascal, say this is 10, this is 10, and this is minus 30, then again there's a 20 kilopascal at C position, so this is 20, and D position it is 20. So this is my shear force diagram. Now let's find out the moment diagram, maximum moment from the bending moment diagram. Okay, so the bending moment diagram, if I bending moment diagram, here my clockwise is positive, and I know that my MA equal to 0, MB is MB. So when I take the MB, I will take the load in the left hand side. So the load on the left hand side is 10 kilopascal multiplied by 6 feet is equal to, and it is clockwise, so 60 kilopascal kilopounds feet, and MC is equal to, so MC is, at this point there are two forces on the left side, one is 10 kilopound, another is 40 kilopound, and 10 kilopound actually the distance is 10 kilopound actually 12 feet away from point C. So 10 kilopound multiplied 12 feet minus, so this one is, this 10 kilopound actually create the moment clockwise, and 40 kilopound is moment is anti-clockwise, so it's a negative. So 40 kilopound multiplied by 6 feet, and this is 6 feet away from the point C, sorry, and that is minus 120 kilopound feet. Now MD is 10 kilopound multiplied, so this is my position D, and from this D it is 18 feet away, 18 feet minus 40, keep 12 feet. Now 40 kilopound force acts as position B, and the distance, vertical distance from B to D is 12 feet, plus this 50 kilopound at point C, which is 6 feet away from point D. So 50 keep multiplied by 6 feet, which is 0. So this MD is actually 0. Now if I take these values, and if I draw my moment diagram, so it is 0 at A position, and its unit is keep feet. It's 0, and B position it is 60. Okay, now at C position it is minus 120. This is my C position, so minus 120, Okay, and at D position it goes to 0. So this is 60, this is minus 120. Okay. So the maximum bending, the maximum moment is 120. Okay. So from the SFD and BMD diagram we learn that from this SFD and BMD diagram we found my Vmax maximum shear force is 30 kilopound, right? My maximum shear force is 30 kilopound. So actually this is, remember, from my, and my maximum bending moment is 120 kilopound feet. So Vmax kilopound Mmax is equal to 120 kip feet. We are going to convert it to the kip inch. 120 kip into 12 inch means 1440 kip inch. Now our section modulus, required section modulus is M max and sigma allowed. So M max we learned is 1440 kilopound inch, and sigma allowed is given, actually it is given in our problem. Sigma allowed is actually 24 KSI. So 24 KSI. So that means it is 60 is required, 60 inch cube. Now the next we need to look at a chart. Basically it is in appendix B. So this is the there's section modulus. So if you look at this column, so this is an actually W flange or wide flange, and this column is section modulus. Okay, and this is your design. This is the designation. So if you see W24 is the number of a particular W section, and multiplied this cross 100, 494, 84. This is the weight per the pound per feet. Okay, and these are the dimension. This is the total area. This orange color total area is A, and D is the, they call the depth, and web thickness. This section is called web, this section, and width BF, and the thickness is TF. So all the values you can find in your appendix B, page number 804. So we are going to look at that which W flange, which W section has value close to 60. So there are many W section has the value close to 60. For example, W1840, it has is equal to 68.4 inch cube, and also W1645, it also is equal to 72.7 inch cube. There's a W8 into 67, it also is equal to 60.4 inch cube. So I'm going back to this chart. So W1840, if you see, W1840 is 68.4, which which I wrote just, yeah. So this is W1840, this is 1840 is 68.4 here. So you can so once you get these values, so there are multiple sections actually close to these values. For example, W867 is 60.4. So we need to choose several which has a which value is closer to required section modulus, and after that we'll decide which one among those selected, which one you select finally. So we are going to select W1840 because this 40, 45, 67 basically the weight per unit length. So this is 40 pound per feet, this is 45 pound per feet, and which is very close to S is equal to 60, which is 67 pound per feet. So this, if we select W867, is going to be bulky, so we are going to select W1840. So W1840 W1840 is selected. Okay, now the next, once you've selected the W814, so you have the selection. Now you need to check whether this selection is good enough to meet the design criteria. Remember, in our problem we said that shear stress, allowable shear stress is 14.5 ksi. So next we are going to check whether this meets our design criteria or not. Now so the shear stress, we know the shear stress tau average is V max by AW. Now what is AW? AW is, if you go back here, AW is actually the area, the web area. So that means if this is my section, so this area is web area, this hatched area is web area, and this is Vmax. We know Vmax is equal to 30 kilopound, and AW is, and this is actually TW, and this is D. So TWD multiplied TW, and these values, this D and TW value, we can get from our selected section W1840. So D is 17.90 and TW is 0.315. So if I plug this value, 30 kilopascal divided by D is 17.90 inch and 0.315 inch. So resultant is 5.32 KSI, which is smaller than this tau allowance, which is 14.5 KSI. So if you select W1840, if you select W1840, if you select W1840, your average shear stress is 5.32 KSI, which is smaller than that allowable shear stress 14.5 KSI. So I hope you will understand today's lectures, and so solve these problems and exercise the homeworks I will assign. Exercise the example problem 11.2, 11.3, and I will assign a homeworks. That's all for today. Thank you very much.